Good evening. Today we're going to go over the alpha helix model and the leucine zipper domain. Um, Basically, a leucine zipper domain is comprised of two long alpha helices. Hydrophobic side chains extend out from the helices into the space filled between them, and oftentimes these hydrophobic side chains are leucine, and that's why they're called a leucine zipper domain. The hydrophobic side chains are packed tightly between the two helices, which gives the structure its stability. The extensions of the two leucine helices straddle the DNA major groove. As you can see, the two leucine helices straddling this piece of DNA on the bottom here. The side chains from both helices extend into the groove to contact both DNA bases. Specifically, the interactions between the side chains and the DNA bases are hydrogen bonds. So here we have, the arginine base making contact with the guanine base. But the most important interaction will be between lysine and glutamate, um, as there is a electrostatic interaction between them and a hydrophobic interaction between the leucine molecules that give this leucine zipper its um, stability. This creates a protected area for the leucine zipper to develop, as the stability of this complex is protected from the surrounding aqueous media. And as a result, when the hydrophobic molecules come together, there is there is a little pocket basically that shields off this molecule from the aqueous environment that will otherwise disrupt the formation and the interactions. Additionally, um, a lot of these molecules, such as lysine and glutamate, have opposite charges, so it helps them attract. A possible residue that could replace leucine in the leucine zipper would be isoleucine, because isoleucine is equally hydrophobic as leucine, also has the same side chain length and the same molar mass. The molar mass is 131.2 grams per mole. I've drawn out the model of isoleucine, the structure. Um, it could help maintain the same hydrophobic environment as leucine. Um, the R groups are basically isomers of each other. So, a possible residue that could destabilize this structure would be serine, because serine is actually hydrophilic, and being hydrophilic, it will break down the hydrophobic interaction between the lysine uh, chains. By introducing serine into the hydrophobic amino acid sequence, it would cause the amino acids to be exposed to the aqueous environment instead of staying together. And here we have the structure of serine, as you can see. Um, any structure that could also replace the interaction of lysine and glutamate would probably be a structure like aspartate and arginine. Um, they can possibly replace the interaction of lysine and glutamate because aspartate is acidic and arginine is a basic side chain. So both of these could interact with each other, similar to how um, lysine and glutamate can interact with each other. And here I have drawn the structure of aspartate and the structure of arginine.